Well, I'm going to jump right in. We're going to do two things with this presentation. First, we're going to talk about the stream functions pyramid framework, and then we'll move into a tool that was developed out of the framework called the stream quantification tool. I'm going to give both parts of this presentation. They'll both be pretty high level looks because there's a lot of information on both. So if you do want more detail, you can use these two documents. And I put my web page here where you can get both documents, but I could put these documents on the resources page as well. One advantage to this web page and the stream quantification tool page is you can see other stream quantification tools as well if you want to. All right, so let's start with the stream functions pyramid. And I guess first thing is just know that this is a concept. It is a way of thinking. It takes all of the stream functions that we've been hearing about and talking about this morning and kind of simplifies it, puts it in a hierarchy and a way of thinking that was developed with the stream restoration practitioner in mind. And I think you'll see that as we move through some of the applications. So at the very base of this pyramid is geology and climate. And so this acknowledges that these stream functions will look different, how they play out based on different parts of the world. So this is why streams in Alaska look different than streams in North Carolina, different geology, different climate, but these functional categories apply everywhere. And so there are 5 functional categories, and that's an important term to remember as we move through here, functional categories. So those categories are hydrology, hydraulics, then geomorphology, and then physicochemical. There is a C in there, physicochemical. And then on top is biology. And within each functional category, there's a functional statement. And so the functional statement for hydrology is the transport of water from the watershed to the channel. And then once water gets to the channel, then we have the hydraulic functions. And that is the transport of water in the channel, on the floodplain, and through sediments. Once water is in the channel and on the floodplain, it can do work. And that work is expressed in the geomorphology category. So the transport of wood and sediment, and really you could add storage there as well, or even supply, transport, and storage of wood and sediment to create diverse bed forms. So think habitat there, riffle pools, for example, and dynamic equilibrium. So you could think about channel stability with that. And then finally, on top of that, or not finally, but next would be the physicochemical functions. So now we have the temperature and oxygen regulation, the processing of organic matter and nutrients. And finally, on top is the biology functions, and that's the biodiversity and the life histories of aquatic and riparian life. And it really is intended to be animal life. And I'll get into that a little bit more as we move in and further flesh out this concept. All right, so in terms of just thinking about this structure and how it works, it really is a way to think about if you want to improve a certain function, what supporting functions must you have in order to achieve that goal? And so it's more of a move from cause to effect. Maybe you are a fish biologist and you want to have more fish in your project reach after restoration than before. Well, you can't just go out there and dump a bucket of fish into a degraded stream and say you are restored, have a nice life, right? Like certain things have to be there, habitat, temperature we heard about. And so really it is a diving down approach. If you start with biology and you say, we want to have this native fish, then you might say, well, what limiting factors do we have in physicochemical, geomorphology, hydraulics, and hydrology that would keep us from meeting that goal? I was listening to the earlier presentation with wetlands and beavers, which is an excellent presentation. And beavers always come up right here because people will say, well, what about beavers, right? Beavers are an aquatic life form, they're biology, but they can affect all the way down into hydrology. In fact, that's what we saw with some of those channel evolution pictures. And that is correct. but that's not the way to think about it with this concept. This is not meant to be a concept that talks about the interrelationship among functions, but rather, if you want something, what do you have to have in order to achieve it? So the beaver example would go like this. If you want to have beavers in your river corridor, they are in biology level 5, then what supporting functions do you need in physicochemical, geomorphology, hydraulics, and hydrology in order to support that healthy beaver population? The last thing I'll mention with this thought process is that one goal with this is to help improve the communication between disciplines. Because if you go to a traditionally trained hydraulic engineer who works for a flood control district, they were trained to really only think about those first two categories. How much water is coming from the watershed, and how do I move it in a channel? I want to put the 100-year discharge in a channel. And that will cause problems to the people who are thinking about geomorphology and certainly on up into biology. And so we hope this is a way that the different disciplines can come together and first identify that goal. Do we just want channel stability or in habitat? That would be geomorphology. What do we need to support it? And then on up through biology. All right, so a little bit more like, why do we need this? Who cares? What does this concept do? It was really developed with the stream restoration practitioner in mind. So hopefully you all agree that the picture in the bottom right looks better than the picture in the upper left, but how much better? Like, that's where we're headed with this presentation, is to be able to quantify that lift. And then to be able to link that back to a reference condition and say, okay, how much improvement have we made with restoration? And then how does that improvement compare to reference condition, meaning culturally unaltered or even pristine? And then we want to flip it around and look at it the other way as well. If you had that nice stream, well, what if we did put a transportation corridor through there and channelize it? So if we did that, there would be a functional loss, and we want to be able to quantify that loss as well. All right, so that's really just the pyramid and the concept. And this, we do flesh this out into a framework to include function-based parameters within each of those functional categories. And then we link metrics, or we attach metrics to those parameters. And then attached to the metrics are reference standards that are put into categories of functioning, functioning at risk, and not functioning. So I'm going to walk through the parameters, introduce you to the metrics, and then talk a little bit about reference standards to round out the conversation about the framework before we move to the SQT. All right, and I'm going to do this part quickly because we just don't have time to go deep into the parameters. I'm just going to show you an example of the parameters that are by category. What you see here is a complete list of parameters that have been used so far for hydrology. Again, these are all parameters that will help us understand or describe the functional statement in that category. So this would be for hydrology. The parameters in black were in the original framework document. The ones in red have been added as we've developed SQTs around the country, and the ones highlighted in yellow are included in the Alaska SQT, Stream Quantification Tool. So that was hydrology. You can see hydraulics. Two that are in Alaska are floodplain connectivity and flow dynamics. And then I'm going to kind of pause here because I just want to kind of re-emphasize the importance of floodplain connectivity. I won't belabor the point because you've heard it several times already today, but it really is a key parameter. I generally tell people that the #1 job of stream restoration practitioners is to give floodplains back to rivers. So if you're talking about single thread channels or multi-thread channels, it doesn't matter. Like, reconnecting the stream to the floodplain is quite key. You can see this example of a stream meandering through the center of the valley, nice floodplain connectivity. Here's a restoration project, and then the big flood going through that project And you can see how low that energy is because we're dissipating energy on a floodplain. So keep that in mind. Of all these parameters, floodplain connectivity, I would argue, is the most important. Quite a few parameters in geomorphology. You might notice here that riparian vegetation is in geomorphology. It is here because in order for riparian vegetation to thrive, it has to have the appropriate hydrology and hydraulics. So it's supported by those categories. It directly affects geomorphology through channel stability, and then it supports the higher functions of physicochemical and biology. All right, so just some key parameters for assessing geomorphology, and all these parameters are important. I just, in a short presentation, I wanted to focus on some that I felt like were key. And really, we always share that these are kind of key parameters for both assessing a given category and also being able to see that functional uplift as a direct result of restoration, or the loss as a result of some impact. So the three that are extra key for geomorphology are bedform diversity. And if that is not a familiar term to you, think about it as in-stream habitat, riffles and pools. You could put runs and glides in here as well. The heterogeneity of the bed. And then riparian vegetation. We've already heard quite a bit today about the importance of that riparian vegetation. I'll just reiterate it here with providing that channel and floodplain stability. Habitat contributions both to the channel and outside the channel, and then organic matter contributions to the stream, and certainly more. You could put comma, etc. And then finally is lateral migration. And that's really having the appropriate amount of stream bank stability. I think we also heard that, bank erosion is not a bad thing, but too much can be a bad thing in terms of sediment supply, excess sediment supply coming into the stream. So through geomorphology, we have what we call the big four. Like, these are, again, from a stream assessment and restoration perspective, if we can get these four parameters right, we have gone a long way towards having a successful project. So these two pictures are pictures of stream reclamation projects in the Alaska interior. And you can kind of see these four parameters at work. I will note that both of these pictures are in confined valleys, actually colluvial valleys. And so you don't have wide floodplains here. But if you look at the picture on the right, you can see the transplants, and just outside the transplants, you see a floodplain bench, and that counts as the floodplain connectivity. So there's still a lot of effort here put into making sure that the channel depth and the channel size is appropriate so that the right amount of water is in the channel, and then the rest of the water goes out onto this floodplain bench. So that's the floodplain connectivity. The bedform diversity is a little bit easier to see with the picture on the left. Like, that was all constructed, and you can see this cascade coming into a step and a pool. That's the appropriate bedform for that type of stream. This is, as you can tell, a higher gradient stream. So it's not going to be a meandering stream. It's not going to be a multi-thread channel, more of a step pool channel. And so that's the bedform diversity that would be appropriate for that setting. And then the third is that riparian vegetation, just really critical for providing the bank stability and the lateral stability. And then that last one is just that, the lateral migration or stability. If you made me do a big three, I would eliminate lateral migration and stability, because I could almost argue that if you get the first three right, floodplain connectivity, bedform diversity, and riparian vegetation, your lateral migration will come. But we do generally call these the big four. All right, so that's through geomorphology. We still have two categories left and quite a few parameters. So here are the physicochemical, and the Alaska SQT has temperature, turbidity, and for the very first time, we have diatoms as a parameter for kind of helping us understand some of those physicochemical processes, really a bit of a water quality surrogate. And then finally on top is biology. And you will notice that the two parameters that are pretty much always included when using this framework or using the SQT are macroinvertebrate communities. And just want to highlight that here, like that. We really do mean animal life forms. You saw that we put riparian, veg, and geomorphology. So all of these are kind of working together to provide the aquatic animal life. And to date, we have focused on macroinvertebrates and fish, but this could certainly be expanded to include amphibians, mussels, other aquatic life. And I would actually love to see that. Hasn't happened yet, but it would be cool to see happen. All right, so those are all the parameters. So I'm not going to dive deep into this. I have the big four highlighted in bold. I just want to make the point that attached to every parameter are metrics or measurement methods. That is what we're going to quantify as part of that parameter. So you can kind of peruse this list of metrics. I'm not going to go through them here. I just, again, want you to know that every parameter must have at least one metric, and they can have more than one. These parameters and metrics are all included in the Alaska Stream Quantification tool, and there are more for physicochemical and biology, but I'm just going to focus on hydrology through geomorphology. All right, and then after the metrics come the reference standards. So these are divided into three categories. We're putting it into buckets of functioning, functioning at risk, or not functioning. So remember that every metric must have this reference standard. And we're going to do that in the SQT by developing reference curves, which I'll get to in just a minute. So sort of begs the question, well, what is functioning? Functioning in this framework and in the SQT means high functionality for a given metric and parameter. So think culturally unaltered, or even the high end of functioning as pristine. So there are actually quite a few different applications from the framework. Function-based assessments is one. The stream quantification tool, which will be the rest of this presentation, is an application of this framework. There's also discussion to help people develop debit and credit determination methods as part of compensatory stream mitigation. And really my favorite, which is I'm not going to talk about today, is the development of goals and objectives and restoration potential. So we'll end the presentation with just an introduction of the stream quantification tool. I do want to just let everybody know that this was a multi-agency endeavor to develop this. It took about a year to do it. So all of these agencies that you see came together and developed steering committees, technical teams, and worked through a process of taking stream quantifications tools from other parts of the country and this framework and developing a specific SQT for the Alaska interior. So that's why you see this SQT INT. It's for the interior of Alaska. So I've used this SQT term, quite a bit, but I haven't really defined it. And so what is it? What is this stream quantification tool? Well, first of all, it is a spreadsheet tool. It is a calculator. It's a spreadsheet tool as a calculator that's designed to show stream condition improvement or loss from stream restoration and permitted impact activities. And I think importantly, one thing that separates this maybe from other assessment methods is that there is a focus on reach-based activities within the stream corridor on stream conditions. So we are wanting to acknowledge that practitioners are going to come to the stream and do some activity, but how do those activities change stream condition? We want to be able to capture that. The SQT does include components of restoration potential and a way for people to articulate their goals and objectives. So in Alaska, the primary application currently for the SQT is the interior. There is a push or a start now on a north slope SQT that is just getting started. So the one that's available is for the interior. Currently, it does have a single thread channel focus, wadable streams, and non-glacial valleys. So we do hear, everywhere I work, we do hear this interest in more in the multi-thread stream wetland complex, and we'll get there. Like we're getting there, but we're not quite there yet. And for the interior, I don't think it really is that applicable, at least for where most of the work is currently happening. It is more in those confined alluvial or colluvial valleys, which would be single thread channels. Just keep in mind that this is a corridor assessment. So back to Matt LaCroix's comment this morning about the importance of the corridor. This tool is looking at the channel, the floodplain, and the riparian area. And if you were doing or applying this to road crossings, then you would probably do 3 reaches. You would look at an upstream reach and how that might be impacted by the culvert, if it was a culvert or the crossing. The second reach would be the crossing itself, and then you would look downstream of the crossing. All right, so I'm going to end with just how the SQT scores. And it is scored with these reference curves. So every metric in the SQT has a reference curve. The x-axis is the field value. And so the example here is for pool depth ratio. Pool depth ratio is a metric within Bedform Diversity parameter. The field value you could think of as the assessment output of that metric. So you go measure pool depth ratios, you process that data, the field value is the result. That's always the x-axis, is the field value. The units vary a lot because it varies on the assessment method. The y-axis is always from 0 to 1. 0 represents no function. 1 represents pristine. This is the condition score. 0.3 represents the break between not functioning and functioning at risk, and 0.7 between functioning at risk and functioning. And then the regression lines that you see are essentially the model from the data, the regionalized data of pool depth, to convert the field values into the index value. So the curves themselves look very different from metric to metric, but the process in developing them is the same. I also just want to mention stratification. So you may be sitting there picking up on the fact that, hey, some streams have floodplains, other streams do not, and they have these floodplain benches. That's going to affect things like bedform diversity. And you are absolutely correct. And so the way we deal with that, to be able to assess lots of streams in one tool, is through stratification. And so this one is showing a pool spacing ratio, which is another metric for bedform diversity. And in this example, our reference stream type is a C, which would be a meandering stream. And therefore, it's going to pull the reference curve for C stream types. If the reference was a B, then the SQT would pull that upper curve, which would be a B stream. You can see they're very different. And so this is just one way, or the way, the SQT deals with variability among a region by metric. All right, so lastly is the scoring. It's a really simple method for scoring. We've already talked about the metric field value. That's like the assessment outcome being converted to that metric index value, the 0 to 1 by metric. That is simply averaged to get a parameter score. The parameters are averaged to get a category score, like hydrology through biology. And then there's a twist. At the very end, they are weighted and summed. So here's the weighting. Also very simple. Every category is just weighted by 0.2. There are 5 categories, so every category is 20% of the total. And the reason we do this is that you do not have to assess physicochemical and biology. They are optional. But if you do that, then you would if you only assess through geomorphology, your score would cap out at a 0.6. If you added physicochemical, it would cap out at a 0.8. And then if you do go all the way through biology, you'll get the full 1.0 as a max. So to put all this together, the scoring, we talked about the condition score, that's that index score. And then we multiply it by stream length as our unit of measure, and that gives us functional feet. And then the change that we're looking for, because we are looking at, what is the change after restoration or impact versus existing, is we just subtract that. So the proposed score or after score minus the existing gives us that functional change. It is then reported in 3 different ways. We can roll it up by parameter, by functional category, or the one that's used the most is the overall condition score. And then we add a little bit of information to that score and tell you whether it's a perennial stream, intermittent, or ephemeral, and the stream order. That just acknowledges that not all, if you get a 0.7 as your overall condition score, that doesn't mean it's applicable to all different resource types. A 0.7 for a perennial is different for an ephemeral. So we just want to acknowledge that. And then there's output for monitoring. So just going to end with a few kind of photo examples. So here's a before and after project. You can see the existing score was 0.19. Existing length is 972. So the product of that is 185 functional feet of a second order perennial stream. The proposed condition 0.65, proposed length 1280. So that goes up to 832. And then the difference is 647. So that means after restoration, there was an additional 647 functional feet. And then
wrapping up here, Will, but just wanted to give you a 2-minute warning there. Thanks.
Okay, I can do it in 30 seconds. So yeah, so this is just output. So you'll get this output as part of the SQT. You can get it by parameter. You can see what parameters were assessed and how much lift occurred. So red is not functioning, yellow is functioning at risk, green is functioning, and you can see the actual condition scores. So by parameter, this is one of my favorite outcomes. And then there also is a monitoring component. So you could use this to get your existing or before, your proposed, that's what your design is, what the as-built was, and then however many years of monitoring that you have. And at the very end, it'll track those condition scores and functional foot scores. So you can see that in this example, the prediction was that they could get a condition score of 0.51 and a functional feet score of 561. And by year 5, they achieved that, but it took time. And so that, you're able to monitor trends with the tool to see how long does it take, to get to that target. All right, so with that, I will stop.